Hello everyone, and welcome to a little discussion of vector addition using the computational method of components, right? Or the component method, if you will. We did this last year. You've done this already a bit, but I just wanted to kind of do a little bit more high end of a problem and along the way throw in a little of our new unit vector notation. So here we have two generic vectors, which I am calling A and B. From context, specifically the units, you can tell that these are two velocity vectors. A is a 10 meter per second velocity at 25 degrees, and B is a 20 meter per second velocity at 45 degrees. And I want to add these two together. So I want to see what the net or resultant velocity of these two would be. How fast and in what direction, say, would the object actually end up going? Now, you might be saying, oh, okay, well, we can just throw an arrow in here from one to the other. But can we? This is vector addition. And how do vectors look? How do they combine when you're doing vector addition, right? It's supposed to be head to tail. This is not head to tail. So these are not drawn as A plus B. This is more of a, maybe this is the boat and it's going this way and the water's flowing that way, or this is the plane and it's flying that way and the air and the wind is blowing that way, and we want to see what the net effect is, right? So this is not a vector diagram right now. We have to create a vector diagram. We have to draw the vector addition, which we draw, of course, by drawing one vector. So there's vector A at the 25 degrees. And then head to tail, we will add vector B. Now again, of course, my drawings are all to an internal scale. You're just sketching, right? But it does help if you label the vectors, if you put the angles on the drawing so that you can see them. Now, depending on how good your drawing is, you might be looking at this angle here and saying, hey, is this a 90-degree angle? No, it's not, right? These are two parallel lines cut by a transversal, so alternate interior angles are congruent. Hence, if that's 25 degrees, this little one is 25 degrees. And since this is 45, that's 45. And 45 and 25 is 70 degrees. So this is not a right angle. The resultant goes from the tail of the first to the head of the last. I'm going to call this V because it's a velocity. But this is technically A plus B, right? Vector addition, not regular addition, right? It's not 10 plus 20 makes 30, right? It's 10 at this angle and 20 at this angle make that, right? Vector addition. So I'm going to call that V. Now, problem is, of course, is that this is not a right triangle. Right? So what are we going to do? Well, we need to create a right triangle with this resultant velocity as our hypotenuse. Say maybe something like this, right? As this vector seems to be going to the right and down. Right? If we had this right triangle, finding the hypotenuse, the resultant velocity, would be fairly straightforward, as we will see. But we have to create that. So how do we do that? Well, hopefully you remember that we start out by breaking each vector up into its perpendicular components. Since we're in two dimensions, we're going to use positives and negatives, right, for the components so that we can keep track of directions. So here's A. At that 25-degree angle, we draw the horizontal component first. That's A sub x. The vertical component second. That's A sub y. There's, of course, a nice right angle in there. Right? If we want to use the more mathematically sophisticated method of figuring out our positives and negatives, we can use 205 degrees from 0. Remember that the positive horizontal is always 0. You can use the 25 degrees, but then you have to get the positive or negative out of context. Third quadrant, this is to the left, this is down, right? But if you use the 205, calculator will spit it out for you. So, of course, we're going to use a cosine to find A sub x, as it is the adjacent side. So hypotenuse cosine of the angle works out to be a negative 9.06 meters per second. You might be saying, wait, why did you have 3 sig figs here when there's only 2 there? Because I kept an extra one until the end. I don't want to overround and overround and overround, right? So I'm going to keep an extra sig fig lying around. I'll round when I get to my final answer. Of course, to find AY, we'll just use hypotenuse sine of the angle, which is also a negative because it's down, 4.23 meters per second, extra sig fig. Same idea for vector B. Here is the horizontal component of vector b, b sub x. Here is the vertical component of vector b, b sub y. The angle from 0 would be 315 degrees. Sure, you could take this 45 and then that would be 45, and you could do it that way, but again, you would then have to get positives or negatives from context. So, if we're going to do the horizontal component here, that would of course be hypotenuse cosine of the angle because it's the adjacent side. And we get 14.1 meters per second. And then the y component would be the sine, right, of that angle times the hypotenuse, in which we get negative 14.1 meters per second. Now, did you catch that? Right? Some of you might have been inclined to go, oh wait, that's a 45-degree angle. This is a 45, 45, 90, which means that the two legs have the same size, right? It's an isosceles right triangle. However, this is not geometry class. This is vector algebra, right? So yes, they have the same magnitude. So yeah, you could have not even done the math here, but they are not in the same direction. Right? This one happens to be negative because it's down, so don't get sloppy. It's not geometry, it's vector algebra. Now that we've broken each vector into components, and by the way, you can do this for 2 vectors just as easily as you can do it for 20 vectors, just take longer. We then combine the x's and the y's to find the perpendicular components of our resultant. So, I remember called the resultant v for velocity. So the x component of our resultant is the vector sum of the x components of our 2 vectors. That's a negative 9.06 meters per second and a positive 14.1 meters per second for a grand total of 5.04 meters per second. Note positive. The y component of our resultant velocity is the vector sum of the vertical components. Negative 4.23 meters per second and negative 14.1 meters per second for the even larger negative 18.33 meters per second. Now, if you want to write this answer in unit vector notation, you've got all you need to know. Remember that x's are I caps, y's are j caps, and if we were in 3 dimensions, z's are k caps. So we could write it thusly, where the velocity is 5.0 meters per second I cap minus, because of this negative sign, 18 meters per second j cap. That might be a perfectly good answer. You know, if this is a multiple choice, maybe they've written their answers in unit vector notation. Note again how I have grouped the units with the number, right? And then the unit vector, which remember has a magnitude of 1, it's all about direction. It just sits outside. So I cap, j cap. Now, more than likely, though, they're going to want the answer in polar coordinates or in magnitude and direction, right, is the way we usually say that. Technically in math, you call those polar coordinates. So we need to draw the resultant vector diagram from our components. Since the x component is a positive 5.4 meters per second, it's going to be drawn to the right. Since the y component is negative, it's going to be drawn down. Notice how we are adding the 2 components in order to make the resultant velocity. And note, we've got a right angle. Check this out. So look at this. Remember, I'm drawing everything to a nice internal scale. So if we compare this to this, isn't it the exact same diagram now, except now we know what the components are? Ah, clever. So if you'll notice here, this diagram, the only purpose of drawing this diagram was to really give us an idea of what our answer should be. Kind of like what quadrant we have and, you know, what the right angle, what the right triangle vector diagram should look like. So, you know, it's a good idea to draw it, right? And if you sketch it well, it should give you a good idea of kind of what you're looking for in the end. But there's no substitute for actually breaking everything down in components, adding the x's, adding the y's, right? Redrawing your resultant vector diagram. Now that we have this, it's pretty straightforward. If we want the magnitude, we just do a Pythagorean theorem. Now I'm going to round off to 2 sig figs, 19 meters per second. We need an angle for the direction. Don't forget the direction, right? Always at the tail of the resultant, so I might find that angle. I would do that with an inverse tangent of opposite over adjacent and get an angle of 74 degrees. Putting that all together, you'll notice that this problem did not have north, south, east, and west in the problem statement. Usually that would mean don't use north, south, east, west in your answer. Okay? So that means we're going to use counterclockwise from 0 notation. So 2 ways. We could go this way around, which would be negative 74 degrees, or we could go this way around, which would be 360 minus 74, or 286 degrees. Personally, I don't care which one you use. If this was a free response problem, they wouldn't care which one you used. If this was a multiple choice, you would, of course, have to choose the answer that they gave you. Right? They probably wouldn't give you both. They'd give you one or the other. But you should be able to figure out both of them, right? So again, counterclockwise from 0 notation. So there was really nothing new here in this problem from what we did last year, with the exception of writing it in unit vector notation if that's what they ask for. Generally, though, they're probably going to want magnitude and direction because it's kind of more meaningful, right, as to where it actually is and how fast it's going, or displacements or force vectors or whatever it is. Right? So let's do a second example, except this time I want to find the displacement a car travels if it goes first this and then this. But notice I have drawn them not in polar coordinates or with magnitudes and directions, but rather I have drawn them in unit vector notation. So actually what's been done here is they've done a lot of the problem for you, because you actually already have the horizontal components for vector A and vector B. So if you want to add them together, our resultant displacement would be the vector sum of A and B. We just have to work with the components. Okay? And vector algebra, in this case, works like regular algebra. We can group like terms. That means we can group the 2 I caps together, and we can group the 2 j caps together. This is exactly like what we did back here when we grouped the 2 x components together to find the x component of our resultant, and the 2 y components together to find the y component of our resultant, except we're doing it in unit vector notation. So we group the 2 I caps. Notice I put these inside of the parentheses. 3.8 meters and a negative 6.1 meters. Don't forget the minus sign. Right? And then we've grouped the 2 j caps, or y components if you will. Negative 2.4 meters. Don't forget the negative. And a positive 1.3 meters. Put those together. In unit vector notation, we simply have negative 2.3 meters I cap minus 1.1 meter j cap. But I didn't ask for unit vector notation, but we can do it. Right? I asked for magnitude and direction. So we now skip kind of to the last steps of our previous problem. We've now got the components, so let's draw the resultant vector diagram and do the basic right triangle trig. So since the x component, I cap, is negative 2.3 meters, we'll go to the left. And the y component, j cap, negative 1.1 meters, is down. And again, I'm drawing to an internal scale. Notice this one's roughly half, right, the length of that one. So our resultant, going from the tail of the first to the head of the last, is our displacement. Right angle in between, head to tail vector construction, because you are adding these 2 vectors together. Right? So the magnitude of the resultant displacements, just a quick Pythagorean theorem, about 2.5 meters. The angle here at the tail would be the inverse tangent of opposite over adjacent. And of course, please remember we are in degrees and not radians. Common mistake. And you'll get 26 degrees. Now again, this problem didn't have north, south, east, west. If it did, this would be 26 degrees south of west. But since it doesn't, we have to use counterclockwise from 0 notation. 0's over here, the positive horizontal, so we need to go around. So that would be 90, 180 plus 26, which is 206 degrees. I suppose if you wanted to, you could go 90 and then to here, which would be, let's see, 180 minus 26 is 154 degrees, I think. Sounds right. But anyway, probably easier to go this way around, right? So note that if you're given a problem in unit vector notation, you're actually most of the way through the problem because you already have the horizontal and vertical components. If this was three-dimensional, if there was a k-cap on each of these, right, you could just do this again, but with k-cap vectors out here. In that case, they probably would want an answer in unit vector notation because they wouldn't ask you to do this because you actually need two angles and it's hard to draw because it's three-dimensional and all that jazz. Right? So I haven't really seen them ask something like that. So here's a little review with a little addition of unit vector notation of the component method of adding vectors.